Parametric equations involve using the third variable t to rewrite a function in terms of t. And that t is known as the parameter. That's why they're called parametric equations, because these other values depend on t. So in this particular example, we have two parametric equations, x of t and y of t. And I want you to think of that x of t like we typically say f of x. We say it's a function of x. Now we have x is going to be a function of t. X depends on t. And so what we typically see with these is we see problems that ask us to eliminate the parameter. And so instead of writing in that function notation, the first thing I'm going to do is I'm just going to say x equals 4t minus 8. And then I'm going to say y equals negative 3t plus 5. Hopefully from your context clues, you're concluding that eliminate the parameter means we need to get rid of the t. We don't want a t in our final equation. We're going to convert this back into a typical Cartesian equation. And so what we're going to do on problems like this is we're going to isolate the t and then substitute it in for the t in the other equation. That's going to substitute it out. So if I look at this example right here in red, what I'm going to do is I want to isolate the t. So if I have x equals 4t minus 8, I'm going to add 8 to both sides, and I'm going to divide by 4 on both sides. If I wanted to simplify that a little bit further, I could say that's x over 4 plus 2. So I've rearranged my x equation in terms of t. But now I'm able to take this value right here, and we're going to substitute in for the t in our second equation. So if I have y equals negative 3t plus 5, all we have to do is simplify this equation. I'm going to start by distributing my negative 3. Y equals negative 3/4 x minus 2/3. And then I'm going to bring down my plus 5. And then all we need to do is combine our like terms. We have negative 2/3 plus 5. If I got them in with a common denominator, that'd be negative 2/3 plus 15/3, which those would add together to be 13/3. This is those same equations with the parameter eliminated. This on a graph would look the same as these on a graph. Now we're going to do two more slides of examples, and they're going to get harder and harder. We're going to first look at some that are quadratic right here. And so on these, I'm going to do it the same way. I'm going to start by rewriting it, not in that function notation, but just say x equals 2t and that y equals 4t squared. And you can't always do this, but I like to solve the x equation for t just because it makes for one step less later on. So if I bounce over here to the right and I divide by 2 on both sides, we get that t equals x over 2. So if I take that x over 2 and substitute in from my other equation, we'd have this. Y equals 4 x over 2 squared. And now let's just do some simplification. And then 4 over 4 cancels. Y equals x squared. So it looks like this is just the parametric form of our quadratic parent function. Now, let's do this one. First, rewrite it without function notation. And I'm going to take one of my equations and solve for t. So I add that 3 on both sides. We can now substitute that back in. And here's where we're going to have to use a little bit of algebra. We got to be careful here is when we square out this binomial. In order to square out that binomial, you have to do x plus 3 times x plus 3. Almost ran out of space there, but that's going to become x squared plus 6x plus 9. And then I'll distribute my 2. And that's got to combine those like terms right there. So our final form of this is y equals 2x squared plus 12x plus 19. Well, when you think you got a good handle on this, you might end up seeing some problems that have some trig functions in them. These would graph to make circles and ellipses, and these are going to require a little bit of a trick in order to eliminate the parameter. So I'm going to start it the same way. Then what I'm going to do is I'm going to square both sides of my equations. And then I'm going to add straight down. On the left side of my equation, x squared plus y squared is just x squared plus y squared. On this right side of my equation, I have sine squared t plus cosine squared t. Hopefully at this point, if you have the background knowledge that you need, you recognize this is one of our Pythagorean identities. It's just equal to 1. So I can substitute a 1 in for sine squared t plus cosine squared t. And now we have our rectangular form of this parametric equation. We've eliminated the parameter because there's no more t in it. That required a little bit of a party trick to get there, but now you know how to do these, and we can try this next one. So I'm going to start by just rewriting it without the function notation. If you remember, our next step is actually to square both sides. So I'm going to copy that down below this green line here. So we have x squared, and to square this is going to be 16 cosine squared t. And over here, it's going to be y squared equals 9 sine squared t. I'm going to do one more step. Keep in mind, we're trying to create this sine squared t plus cosine squared t that we had in this first example. So I don't really want the 16 and the 9 there. So what I'm going to do is I'm going to divide both sides of my red equation by 16. And then on my second equation, I'm going to divide both sides of my equation by 9. Now, and I'm running out of space a little bit, whenever we add straight down, we're going to have x squared over 16 plus y squared over 9 equals, once again, that sine squared t plus cosine squared t. But we've already established that's just a big old 1. So boom, there you go. This is our form of it. Over here, we had the equation of a circle. Over here, we've got the equation of ellipse, and graphing that is outside the scope of this video. But if you can do these 3 types of problems, you are able to eliminate the parameter.